In this video we're going to be looking at pulse analog modulation. In pulse analog modulation there are three basic types: pulse amplitude modulation, pulse position modulation, and pulse width modulation. In these forms of modulation, the carrier signal is no longer a sine wave that we've been used to seeing, but this time it's a train of pulses, as shown here. Now these forms of modulation produce baseband signals. These can be used to transmit signals over a wire, or they can be multiplied by another carrier signal to be used, say, in optic fibre systems or infrared systems. Now with a train of pulses, just like with a sine wave, there are three things that we can vary. With a pulse train, we can vary the amplitude, the pulse width, or the pulse position. And this gives us these three basic forms of modulation. So what we've been used to seeing at the top is our sinusoidal carrier signal, which you'll recall the spectrum of that is two impulses, one at Fc, the carrier, and one at minus Fc. The spectrum of a pulse train is shown at the bottom here, and it's quite a bit more complicated. It's actually a series of pulses at regular intervals at 1 over t0, where t0 is the periodicity of the pulse train, and the zero crossings of the envelope shown here are given by the inverse of the interval on which the width of the pulses. Now this envelope signal that we can see over here, the envelope of this spectrum is a special function which we call a sinc function, S-I-N-C, and it's simply equal to sine of x over x. So the spectrum of this pulse train is a series of impulses whose amplitude is dictated by this sinc function envelope. We'll come back to this later on. Now when we are doing pulse modulation, what we're actually doing is sampling the signal, the message signal, to make it discrete in time. And when we do that, all we're doing is we're making the spectrum of the signal periodic. So at the top here we can see a message signal, could be an audio signal, speech, and we see its spectrum over on the right hand side. And when we sample it in time at a uniform interval known as the sampling interval, t of s equals to 1 over f of s, we simply make the spectrum periodic with the periodicity equal to f of s. And if we make the sampling frequency lower, or the sampling interval larger, you'll see that the effect of this is that the repeats of the spectrum get closer together. And there's a limit to which we can continue to make that lower. And the limit was found by a fellow called Nyquist, and so it's known as the Nyquist sampling criterion. And that says that the sampling frequency must be greater than or equal to twice the bandwidth of the signal. Fs greater than or equal to 2b. Now we'll be using this later on when we talk about digital modulation as well, but it also applies to pulse modulation. So instead of looking at the entire message signal in time, we're only going to be looking at it at discrete points. Pulse analog modulation, pretty basic. We vary the amplitude of the pulses in accordance with the amplitude of the message signal. And the effect of that is that the spectrum of our PAM signal is spread out over a very wide range, theoretically infinite, because sine x over x never goes to zero, except at the zero crossings. But practically 98% of the power is contained within plus or minus 2 of the zero crossings. So as you can see, pulse analog modulation systems require a huge bandwidth. So why do we bother with them? What do we gain? Well, it turns out that the one and only benefit of pulse analog modulation is the ability to send more than one signal on a channel at once. This is known as time division multiplexing. So we break time up into discrete points or channels, and as we can see here, message 1 is in blue, message 2 is in green, message 3 is in red, and we can combine them all into one signal that gets sent down the channel. Now this is very useful because we might have, let's say, an application like a remote controlled aeroplane where we want to control 2 axes of motion plus speed. So this could be our message 1, message 2 and message 3. And we would be sending those all over the one radio channel at the same time. Of course, there's many other uses for these sorts of things. Time division multiplexing is used in digital telephone systems as well. Many other applications. What about pulse position modulation and pulse width modulation? Well, these are shown here. Let's say we have this sinusoidal message signal at the top and our carrier shown here. The first one is pulse width modulation, and you can see here that the width of the pulses varies linearly in accordance with the amplitude of the message signal. So here, where the amplitude of the message signal is high, we get fatter pulses. And here, where the amplitude of the message signal is low, we get skinnier pulses, or narrower pulses, wider and narrow. And pulse position modulation is where we don't vary the width, but we vary their relative position. So here you can see this pulse is slightly delayed in time. This one's delayed even more. And these ones are advanced in time, where the amplitude gets lower. So these are all forms of pulse analog modulation. Now the spectrum of these ones is similar to PAM. The noise performance of PAM is similar to double sideband suppressed carrier that we saw earlier. And the noise performance of pulse width modulation and pulse position modulation is similar to FM. So the only benefit that we get with pulse analog modulation is the ability to combine multiple signals onto a single transmission medium. Now, as I said, pulse position modulation is used widely in remote control aeroplanes. Very simple, and that's used, or remote control anything really. Certainly the very cheap ones, but more expensive ones might use different systems. Pulse width modulation is widely adopted in microwave radio systems, which are these point-to-point systems that go over sometimes over 100 kilometres. and the analogue form of these was used for many years prior to the introduction of digital systems. And you'll see these in country areas, and you'll also see them often on the top of mobile telephone towers. So that brings us to the end of the analogue modulation series, and in the next series of videos we're going to be looking at digital modulation.